I have to hit at least 20 buttons before it starts. All right, we're ready to go. So, any questions before we start? I think. So, what did we do last time? Can anybody recap?
Hyperplanes.
Hyperplanes. And what did it say?
Like if there are any two convex objects that are disjoint, there exists a hyperplane that passes in between them that doesn't connect, that doesn't touch anything. There exists a if any two convex bodies are disjoint, then there exists a hyperplane separating. We need to we define separated as greater than.
Can somebody make it more precise? You're there, but I just want somebody to deliver the punchline. There's something which is missing, and that's very critical. So what did we have? We had two bodies, let's say two convex, that's x chi1 and chi2. What did it say? What should be the properties on chi1 and chi2?
This would be disjoint.
Okay, so suppose they're disjoint, then what happens? What are we guaranteed?
They're disjoint and convex.
Yeah, convex is given.
Then there will be a hyperplane.
Yes, such that
There will be chi1 on the other side. There will be.
yeah, but can you be more specific is the question. See, one side, two side becomes very difficult, right? Eventually. So how did we define our hyperplane? This is how we can generically define hyperplane. Now, in terms of this, can you say something? Can I state a theorem saying there exists an A comma B such that A transpose X is greater than B for all X belonging to chi1 and A transpose Y is less than B for all Y. That's what the statement I want. See, the less than equal to signs are very important. Possibly they're essentially touching each other. There are more complications than one can actually anticipate. So strict separation is what you are actually saying. That we haven't proved. And that may not even exist. So can you think of disjoint sets where strict separation is not possible? The question clear? That you have two convex sets which are disjoint, but you can't find an A transpose X, A and B such that both these inequalities become strict. So you have to think about something very particular. If you keep looking at these kind of sets, it will be true. So some limit has to be brought in. That gets closer but not touch it.
You're saying what that we want to find into convex sets such that there is
That disjoint, but you can't find a hyperplane strictly separate. We already proven that if they are convex disjoint, we can find non-strict separation. Question is, can you always find something like that? What goes wrong? Why are we asking too much? Is the question clear to everybody? What we are after? We're after two convex sets which are disjoint, but there exists no hyperplane that's strictly separate. So any nice things will not work, but they're not too ugly either. And the hint is that think of some limit.
We could take, for example, as an example.
Yeah, one example is enough to count. See, prove or disprove, one counter example is sufficient.
You can take the sets, open set minus 1, but open set doesn't necessarily be convex.
Open set can be convex.
Minus 1, 0, open interval.
Yeah.
And 0, 1, open interval.
Okay.
So that.
What will happen?
Yeah, but it doesn't go inside the set.
We want to counter example. We want to show that such a thing is not possible. And for that, you'll have to come up with a counter example. That what you're asking for is too much. So we're asking for a counter example where you produce two convex sets such that they are disjoint, but you cannot produce a hyperplane which will strictly separate them. What you produce is that this also works.
So by strictly separate, do both the equations have to be strictly
Yeah. Let's put it that way.
Okay, then
No, that's an example. It works. I'm saying something that doesn't work. You will not be able to.
So that's quantified detail. So -1 to close 0, open 0 to 1.
Okay. Does it work for everybody?
But there is no strict.
See, as I said, some limit has to be brought in. What you're doing is exactly that. So, what did you say? Minus closed or open? This was closed. Right? Doesn't matter here. Here it doesn't matter anyway. And here it was open and let's say closed. Okay. Can you tell me why this works? Sorry. It's not to pin you down, it's just to make sure that everybody is on the same page. Otherwise, I'll do much more explanation. So which hyperplane will not? Can you produce a hyperplane which strictly separates them? Let's do that way. They're clearly disjoint. So the only possibility really is y equal to 0 line. But what happens to y equal to 0? The closed interval actually touches it, so it cannot have a strict separation. So you'll have to come up with some limits. If you take closed from both sides, then they are no longer disjoint. So you'll have to do something of this sort. There are many examples of this type that essentially create regions which are kind of open. You could have used from something we discussed last time. So what was this area? This was xy greater than 1, x greater than 0, y greater. This is what this looks like. Using this, can you create another example? So this is my C. Can you produce a D? Such that they are disjoint, but you can't produce a hyperplane.
X-axis.
Okay.
It
will work for everybody. See, whatever just above X will try, this will eventually cut somewhere. So they're not going to get disjoint. So there are many ways in which you can construct such things. So how you keep extending it further and further. Any line you draw, here, this blue curve will always go under. Which blue is this? So x equal to 0, x less than equal to 0, all sorts of things will work for D. So you can't ask for anything more than this. Was the proof of this theorem clear? I did it in a hurry at the end. Does anybody want me to do it again? I'll be happy to do it. And don't hesitate. Work for me is okay. If you think it will help you, I'll do it again. Otherwise, I'll move on. Tell me, what property did I use? Of course, we are convex and I have to use convex. What precisely, how did I use the convexity of it? Because this we saw is not true for non-convex functions. They're not non-convex sets. So somewhere convexity had to be used. Just tell me that punchline so that I know that you got the gist of it. So we started with thinking of two closest points on these. And what did we produce? We produced something. And I would strongly urge that at least just before the class, read up for the previous class. You can watch the video, it's available, or you can press up your notes, whatever. It's very important because going forward, it's always good to know what we did at least in the previous class, if not in all previous classes. Now remember what we did? We did something. So we took these 2 points, let's call them D and C, which were nothing but the closest 2 points on these two. And we looked at this plane. We defined in such a way that this is the hyperplane, which is perpendicular to this vector. So this vector was D minus C, and this was my hyperplane. Now what did I do next? What did we wanted to show? Which required that the set was convex. So we said the claim is that everything on this side has this A transpose X greater than or equal to B. Everything on this side is less than or equal to B. And when the contrapositive is that suppose there is a point for which on this side is less than B. What will go wrong? That's all the basic idea of the problem. No, so what we did was, let's suppose there was a point U for which f of u, where f is nothing but the hyperplane, is less than 0. What went wrong when I started doing this? What point did I create where I had to use the convexity? I did something starting from this. This is the contradiction hypothesis. That there exists a point u belonging to chi1 for which f of u is less than 0, where f is nothing but my created hyperspace. Or not subspace, or what do I call it? So did something like this. Sorry?
Joining you know that A transpose D, like f of D is greater than or equal to 0.
We didn't use that. Because their convexity doesn't come into picture. The convexity was really to produce a point. It's a linear combination of D and U. So theta D plus 1 minus theta U. Now I know that this belongs to chi by convexity of it. And this point, this new point, had its distance from C. So distance, okay, let me call it dist of, let's call it U tilde. So U tilde comma C was actually smaller than dist of D comma C. Now both simultaneously cannot hold true. That's what we really did. And all of this was created with such a property, just starting from this, nothing else, just rewriting the definition of the hyperplane. So all we created was, because of the convexity, this point lies in chi1, and because of whatever we showed, the distance between u tilde, which is, so we came here without having to look at the convexity. Now, if this was not convex, I could not have claimed that u tilde belongs to chi1. This is always true, no matter what. Just the fact that u tilde belongs to chi1 or not will actually give you the proof. Now, the fact that chi1 is convex, this better belong to chi1, and you're producing a contradiction. So essentially, this gave you this. That was some elementary computations, just looking at the derivative around this point. Okay. And there, the fact that it's convex is very important. Because otherwise, anyway, we know you can't have it. Okay, so now we have seen two things. One, separation and strict separation. Is not possible for arbitrary convex. This doesn't mean that it's never possible. In general, it's not possible. Okay, so what about strict separation? Not possible, arbitrary disjoint. The strict separation for a point X which does not belong to chi and a convex set phi. Can you claim at least this much? Is the writing poor? This we saw by way of example that is not always possible, but it is at least this much possible. Not always possible. Why?
Example I gave it, the left part is just take a simple 0.
The
right part has open 0.
Okay. So now what do I need to insert to get this to work? So if I wanted something like this, what extra condition do I need? Does everybody agree with what he said? That instead of taking the 0, 1 closed interval, if it takes, sorry, -1, 0 closed interval, it just takes 0 as a singleton. Now can you separate the two sets even though they don't overlap? The same thing will happen, right? Essentially the same thing. So what more do I need to add at least here? Okay. What does it mean?
Then said the distance between X and the convex set should be greater.
Okay, so how do I write this? See, X doesn't belong to X, that is clear. You can massage whatever adjective you want to put in front of the convex set X.
So X is of course just the convex.
X is a point. It doesn't belong to X. That's all is given to you.
I meant chi. Chi is the convex set.
Correct.
So if X should not lie on its boundary in the sense that.
Okay, but can you not make it slightly more general than that?
More general than boundary. So
something which is much shorter to write and works.
Shortest distance should be greater than
Possibly might work, but it's too ugly, right? Why not do something, some adjective to the convex set X itself? When are those two conditions?
X is not in the closure of X.
So forget about little x. All you're allowed to do is to add an adjective to chi.
no.
Okay. So closed satisfies all your conditions. Okay, so suppose I throw in the closed. Now can you give me whether such a thing holds? So proof is not the example. Counter, like disproving is okay with an example. Why?
Because then we can like, because X is not inside chi.
Yeah.
And it's because chi is closed, that means that X does not also lie on the boundary.
Okay.
Which means that around X you have a ball outside. Right?
Yes.
So then the distance between X and chi is positive.
Okay.
So take that distance and and make a ball. So then we can have
that will be because from the previous theorem, it would give you strict separation. You have to do something more. The previous theorem only tells you separation, doesn't tell you strict separation.
Right. So we finish constructing the ball first, and once we construct the ball will just the ball and the convex head can be tangential. So and then it will be
that.
no, but like if you want to construct a plane, so the plane needs to be parallel to something.
Right. The previous term gives you something.
Okay.
What do it give you? It gives you non-strict separation. You can use that and construct strict separation.
We can find another point lying in between X and the closest point of chi.
Okay.
And there we have a separating plane which might not be strict.
Huh.
But now X lies.
Yes, so what do? I want strict separation on both sides.
So we find another element where there is no strict separation, but it lies just in between X and chi.
I think, yeah, you guys' ideas are right. You just need to make sure that something happens. Idea is correct. So, should I sketch the idea or people want to have another go at it? It uses the theorem. Without the theorem, it's very difficult to prove all over. Like afresh, it's unnecessary. You should definitely make use of the theorem you prove. But that doesn't give you strict separation. So for strictness, you need that extra work, which is exactly what you pointed out. I will just give words to what you said. And it will also be clear why closeness of X is needed, because otherwise no such ball exists potentially. Okay, so let's, where are my pictures? Okay, so this is in fact theorem. Strict separation of a point X not equal to X and a closed convex set phi is always okay. So here is the point X. Here is my phi. What I'm going to do? I'm going to put a ball around X. We'll call this ball X comma epsilon. So this is standard notation. X is its center, epsilon is the radius, and this is the ball. Now there exists an epsilon such that B and chi are disjoint, right? So there exists epsilon greater than 0 such that B intersection chi is equal to 5. And why is that true? Because of the closeness of X and little x not belonging to chi. Okay, now what should I do? From the strict separation, from the separation theorem, what do I get? This implies there exists A comma B such that this hyperplane is known. Let's give it a name. Separates B and that much I have done. Now I want strict separation. Now just put some things here and there and make it work. So this much is guaranteed by my theorem. So all the languages are on the board. Just give me the basic idea. Now this B and X possibly are have a single hyperplane which touches the, in some sense, I don't have strict separation. That is true. What can I do informally so that I can get strict separation? Just pictorially.
You can reduce the size of the ball.
That's what you should do, because the ball in the worst case is already very close to X. So if I shrink it by epsilon by 2, that's just the simplest way is to go from epsilon to epsilon by 2. Now I have to just make it work. Now why should it work is the question.
You can give a contradiction. Say it again.
It might work. I'm not saying it will not work. Might become messy. But what does this theorem guarantee you? So I can write B, this set B as X plus U such that mod U2 is less than epsilon. There's another way to write this ball. What does the hyperplane theorem tells me? The separation theorem, that any point in B, X plus U, A transpose is what? Greater than or less than, let's say greater than equal to. For all U less than epsilon. This is from my, just this statement. So now where is this the tightest? Where is this inequality the tightest? For what U? See, those are the bad points I want to avoid somehow. Because if it is equality, that's what the worst point U really is, the smallest. So I want to shift it away from that. What should I do? So what U, in fact, minimizes the left-hand side? That would be my worst case.
The U that is like a distance epsilon.
No, so what? Yeah. So what is that exactly? Can you write down the worst U min? U min is the one which minimizes the left-hand side. What will that be?
The boundary of
Which is simple algebra. All you're doing is you're minimizing this. So at U min, this is what it. Now can you massage my AB to produce a new hyperplane, which will give me strict separation? That's all I really need to do. Is this point clear? What is this? There's some length, right? As a function of U, it keeps changing. I'm looking at the U which minimizes this. And that is clearly this.
How are we getting that epsilon?
For all, this is the constraint, right? I can't allow you to be larger than epsilon because I'm just rewriting ball. So all points in ball are writable like this. Translations of x such that the 2 norm of u is less than epsilon. Under this constraint, what is the minimizer of this length? That's all I really need to care about. That is this point. Now use this and massage a comma b such that you get a strict separation. That's all you need to do. So all you need to give me is the new hyperplane. Nothing else. And at that min, the equality is satisfied. So we said something about shrinking by half or something. That's all you need to do. What should shrink by half? Sorry.
Yeah, epsilon should shrink by half. So the hyperplane should.
So now all you need to do is to change a comma b. So just give me the new function.
A can remain the same.
Okay.
B will be equal to b minus u.
That's all. You really need to do that.
B minus
Because what it B is essentially the boundary, how far you stretched yourself. Take it half value. What will happen necessarily? Why should necessarily one be greater than other be less than 0? Now we want to have strict separation. So why should it be necessarily strict if you do that? So B goes to B minus of u min. What happens?
So we were really very close to the diagram.
Where it was.
The plane was very close to that. So now we're just pushing the plane closer.
That's what pictorially that's exactly what is happening. Why do we do strict separation is the question.
So now if we are pushing this plane closer to the ball, then already for like it's not connected directly to X. So I mean it might be touch, it may or may not touch the ball at that.
No, that you have to argue, right? By choice, what you're doing, you have to argue that doesn't touch X.
Okay.
Because there are some if you push too much, you might touch X. So you have to argue that it doesn't touch X, first of all. And at the same time, it is also strictly separating the set chi. So you just have to, what is the property? So a lot of things are given to you by the theorem. The theorem tells you that the A comma B is such that chi is completely on one side, while B is completely on the other side, but the inequalities might be there, which need not be strict. So you have to use again that fact. So you have to massage A and B, and then this one line. That's it. Something is not clear, point out, please.
So we have this plane, which is let's say very close to the diagram.
There is no more very clear, everything on the board. You got A comma B with the property that ball is on one side, chi is on other side. You also you figured out what u min is. That's like the smallest margin in some sense. Now you are essentially only asked to manipulate A comma B. You are correct that you are essentially pushing it to the left. How much should you push? And the resulting separation. That's all you need.
A transpose.
Sorry?
The A transpose chi is less than equal to B.
That was given to you by the theorem. Yes.
Yes. So with B is strictly less than B plus u min by B. So we know that A transpose chi is strictly less than B plus u min by B.
Okay.
And the distance between X and the hyperplane was epsilon. At least epsilon.
Why? That's not true, right? We don't have that, right? What do we have? We have A transpose X plus U is greater than or equal to B. So once you,
So A transpose,
if you put this back, yeah, if you put this back here, what do you get? It should be a minus.
A transpose X is greater than or equal to B.
So this implies A transpose X
Is greater than or equal to B plus
minus epsilon norm of A2 is greater than or equal to B. Just putting it back. So isn't this a new equation of an hyperplane where B has been increased? So now what should I use B as? My new B prime. I can A by 2, half of it is enough. Because then both my inequalities will be simultaneously satisfied. So I'm going to define a new hyperplane where A will remain A and B will go to how much? B plus mod A by 2. Okay, so now give me the punchline that Y. So A comma B is going to A comma B plus epsilon A by 2. Give me the punchline that Y, this hyperplane strictly separates point X around which I drew this ball B and this set Y. Now there is nothing to be done. We just have to observe that we essentially have created the right thing for ourselves. And all we have to use is the first claim, so which came from the main theorem itself, the separation theorem. Separation theorem told you something. Now you created a new hyperplane for yourself. All you have to say is that this new hyperplane strictly separates both. You are not convinced, then let me know. So what did the theorem tell us? There's some property of A comma B, right? What is that property? That A transpose X was greater than or equal to, is that how it is written? Yeah, for all X in B, and A transpose X is less than B for all Y in I. This is what is given to you. Now I'm creating this new hyperplane. You can forget whatever I on the previous board. Just using this and this, can you conclude that this new hyperplane strictly separates the two? So A and B satisfy this.
So it's like
New hyperplane is this.
for Y belonging to chi, then if it satisfies A transpose is less than or equal to B, then it must satisfy A transpose X less than B.
Strictly, because it's only increased, right?
So only B.
Epsilon was greater than 0. So this is definitely increased. And what has happened here? What is the property on point X? So, okay, so there was this, I should not have written for every. Or let me just for the moment allow me to write this X0. Just make it special. All I need is on x0, I need something special. I don't need for every point on the body. That I will not be able to do. So only for x0, what is true? So if you evaluate this new hyperplane at the point x0,
That is a minimum distance. Like we defined over there, this way.
so now I'm only evaluating at what point? The worst possible point, it was B. So moving away, it's definitely positive. Is this clear? Oh, what is happening here? So you should treat this as x0 in my language here. Okay. This was true. And the worst possible U was
Getting equal to.
correct. They will be equal. Now what am I doing? I'm going further away. So U, I'm going half distance back here. Right? That's what I'm essentially doing. The hyperplane is essentially moved from here to here in some sense. What does it mean for the point x0? So think of, you can really think of, look at this affine function, f of x equal to A transpose x minus b minus epsilon A2 by 2. Is f of x0 greater than 0 is all you need to check. Right? I can write that hyperplane equation as nothing but this. Right? All you need to check is this 0 greater than 0 or not? And is it true by our choice? The last equation of the last is completely revealing. It's exactly doing that. A transpose x0 plus u. So just use this. That's what you got by our choice.
Okay.
So this is greater than plus epsilon. So it's strictly greater than epsilon by 2. This is by choice of what we are doing. See, the special point is x0. I'm slightly changing the notation here. X0 here. So by my choice, this is always true. That A transpose x0 minus epsilon norm of 2 is greater than B. So it's clearly A transpose x0 is greater than B plus epsilon this. And if I half it, it is strictly more. And that is all I needed for f of c. So this is true. And this is anyway true. So f of y is less than 0 for all of them. So you get strict separation. Again, I think your intuition was spot on that by the previous separation theorem, you can get non-strict separation and then you start moving it slightly away. And all of this is allowed because the set is closed and convex. If it's not closed, you won't be allowed to do that. That's the proof. Any questions? So sometimes some mechanical things have to come in, but the intuition is more important. At least you'll be able to progress there. To see through what I need to do. Then you put in particular things and make that work. So what I really did was, by a construction of B, we constructed a ball B. That was not given to us. We were given a point x0 and this convex set chi. We created another convex set around x0 such that B and chi were disjoint, and that was allowed because x was not open. Once you have that, then I could use my separation theorem to get a hyperplane A comma B such that it separates. It was not strict. Now all my trickery started. That given the guarantee, can I shift it a little bit so that I can make both of them work? So real foundation is the separation theorem. Okay. Now comes to, I think, the most interesting characterization. Let's write it as theorem. And if I write a theorem, doesn't mean always mean it's true. Okay. We'll possibly create counterexamples say theorem is false. So don't always trust the theorem you have to believe. You don't necessarily have to believe. Always distrust it. Try to find, does it really hold? Simplest example where it doesn't hold, all those things you should keep doing. Let chi be a closed and set. And let S be the intersection of all half spaces that contain chi. What do you think is going to happen? The people absorb the statement first, then you'll worry about whether it's true, false, or whatever. What is the statement? That chi is given to be a closed and convex set. Now look at all possible half spaces that contain chi and take their intersection. And this need not be countable, could be uncountably many, possibly. Question is, what is the relationship between chi and S? So what do you think it is equal? Tangent is not, okay, I don't know, not define tangent plane. What do you want? Normal. That's what you mean. See, we started to talk in the language of tangent and, normal and, so A essentially is a normal vector. And B is what?
Yeah, so it depends on the point.
Okay, so you can go on.
So at each point we can have the tangent plane. That is so, and so all if it's the intersection of all the half spaces, it's going to be the intersection of all the tangent plane. The half spaces that are built by the tangent plane surround each point. So that intersection will be nothing but the Convex. So you could limit for each and every point.
So give me an example. Let's work with examples. This is an important theorem to remember. Even beyond this course, you should remember this. But any convex set is nothing but the intersection of all the half spaces that contain it. It's actually in fact true. Give me an example where this is true. Just to visualize. So think of a pentagon, for example. It's a closed convex set. What is the intersection we are talking about? No, but they will be outside of it. That's not an intersection. This is the best pentagon I can do. Not a pentagon, but assume that this is what. Yeah. So now, which yeah.
Passing through any one line.
This way or that way? This way, right?
The hospital should contain a so.
Correct. So that's too bad. I'm better than that at least. Okay, 1. Two, and blah blah blah. Okay, so now does this also tell you a proof? Okay, one direction I believe is easy. See, when you're trying to say one set is equal to other set, what do? It's exactly. So which direction is easy? What direction is trivial?
X will die inside S. Sorry, chi will die inside of this because it's already half spaces that contain it. So chi will-
It better be inside all the like the intersection of it. So X belongs to S is easy. Other way around is, and we're doing this in a particular progression. So the previous theorem has to say something. To prove that strict separation between point and a closed convexes, we needed the separation theorem. Now we'll need the strict separation between the point and
So if possible, let there be a point that is not.
exactly. So now, given that I have this important tool, how will I ever exercise such a tool?
Then we can construct a hyperplane that strictly separates the point and.
Correct. That is given by the theorem.
But then if there's a hyperplane that's strict. But then the hyperplane.
Maybe drawing it might help. So prove the contradiction is the right thing to do here. It's pretty straightforward.
So suppose there is an element in S
Correct.
that is not in chi.
Correct.
Then we can find a hyperplane that will strictly separate.
Correct. Okay. Fine. Now what? Where is the punchline?
We can create a half plane using that hyperplane.
No, you give that hyperplane. You use that hyperplane itself. What will just give me the punchline? What is the property of that hyperplane?
It contains chi. It will contain chi.
So you have the proof.
Just need to see.
Yes.
These are the power, like this is really the power of the simple theorems, which build upon one after another to give something very important. I don't want you to complete the proof. I just want you to see it. That's all. I'll do it everything on the board. Okay, so let's try to do this. So I'm not going to say anything more than that. So that part is easy. Now let's say suppose there exists X belongs to S, but X not to. So by strict separation theorem, there exists a hyperplane. Let's call it A comma B, H of A comma B, that strictly separates X from okay, I believe this is enough. Can you somebody finish the one line? I just want one more sentence to be written here.
So then this gives rise to a half space that contains I.
Mhm.
X does not lie in that half space.
Give me one sentence I can write. Just like in similar to nothing less, nothing more.
So X does not contain in X is not contained in the intersection of all hyperplanes containing chi.
You have to say that something simpler might work.
X does not lie in a half space.
So what have we done? By strict separation theorem, this hyperplane, there exists a hyperplane that strictly separates the little x from chi. So what has happened in the picture? Let's do a picture also. So this is my x. Let's say it belongs to this S and chi is very bad. This is my chi and there is a strict separation. Right? Now what do you want to call? What is this on this side? This is a hyperplane doing what?
It's giving a half space. Right?
Sorry?
It's giving us a half space.
Yes.
So
So what is this property of H I have to exploit?
it separates.
Yes, that's all I'm given. It's strict separation. Okay.
So then X does not lie in that half space.
It's not a member of that hyperspace. Yes. That is given to you.
But then if it's not a member of that half space, but that half space contains chi. So
Why?
yeah, because like the hyperplane by definition will give two half spaces. One
Correct.
that will contain the convex set and the
Yeah.
other will contain the point.
Agreed. Now contain means what? So this is one direction, right? And this is another direction. So X lies on one direction. Okay.
So yeah, so we have that like in short we have a half space that contains chi but does not contain X.
Yes.
X lies in the intersection of all half spaces.
Correct.
So it should lie in the intersection, it should lie in this half space.
Correct. So that's a contradiction. So what I wanted you to write was the following. That is, there is a half space containing chi but not, and that's not. So essentially X does not belong to this. That's the punchline. So really, if you want a takeaway from this initial part of the course, this is the takeaway. You can completely describe a convex set by the intersection of all the half spaces that contain it. It's not a simple, like, if you don't go down this path, it's very complicated to actually progress. But separation, strict separation of a point and a closed convex set to this, it's a very gentle progression. None of them are difficult, but put them together and you get something very interesting. Okay. Any questions? Okay, so let's do the converse here. Now let's look at converse of the separation theorem. So what did the separation theorem tell us? That if there are two convex disjoint sets, there exists a hyperplane which separates them. What about the converse? If there is a hyperplane which separates two convex sets, are they disjoint? That will be a converse.
Not strict separation, just separation.
Just separation.
Then the two convex sets would have an overlap on the other hand.
Okay, go beyond that.
What is the convex statement?
So the separation theorem statement, you remember that I have two convex sets which are disjoint. Then there exists a
Hyperplane separated.
there is a hyperplane separating the two. Flip it around. Suppose there exists a hyperplane separating the two.
Are they convex?
No, are they necessarily disjoint?
Oh.
The question is clear, right? What are we after? There are many examples where it should not work. You can try any one. So where did you know what additional conditions are needed for it to work? No, you keep it to yourself and think. Let others think about an example. Once you have an example, not you, others have an example, just tell me. There are many, like the simplest things will work. The question should be clear in the mind. What are you after? That will be the answer. It's as direct as that.
We take two circles that are just touching at one point.
Yeah.
And line between.
Why do you have to go so far?
Okay.
Just think of the simplest. Anything you touch should work. Any example you think of should work. So what did you accomplish by putting circles? If you started with just the intersection of those two circles, what would have happened?
Intersection of two circles is a point.
Correct. So think of a single point being defined as two different sets. Can you create a hyperplane which separates, but these guys are definitely identical, so there is no question of being disjoint. So think of a point as the two sets. Chi1 and Chi2 is a singleton point. Can you create a hyperplane which separates?
Because then how can we create?
But what's the definition of separation? So just pay attention to the definition and you'll get it. I'm not asking for strict. That's the point.
Take any point and then take any line that passes.
I didn't say that you can't do that. Example is simple. You don't even have to construct circles and all. So that is out of the question. Now, what do I need to add so that this doesn't happen? I need to add certain more technical conditions so that the converse starts to hold. So why directly it doesn't work is, let's just take Chi1. You take origin essentially. Chi1 equal to Chi2 equal to simply 0. And what is my separation? So this is my Chi1 and Chi2 both are here. Any line passing through them is fine. Will work. X equal to 0, Y equal to 0, whatever. So now what do I need to add additionally so that the converse starts to hold? What went wrong here? That's essentially the question.
We allowed for it to be equal. If it's not allowed, but
No, that is not a good condition. If chi1 and chi2 are
not that, we allowed that the plane could have equal. We allowed.
no, but we still want that to hold. The strictness is even more harder.
Okay, we don't want, we don't necessarily.
Yeah. That will only make it more general or harder. If there is strict separation, okay, might actually make it easier. So think of the following statement I want. Chi1 and chi such that there is strict separation between chi1 and chi2. Chi1 and chi2 is joined.
If there is a strict separation, then you are easy.
You still need something. Now it becomes difficult to see an example. Rather open. You want one of them to be open.
Okay, fine.
Do people see why? Pranab, really? Draw pictures. It always helps to draw pictures here. Suppose one of them is like both of them are closed. What will be difficult to prove?
You are saying strict separation is not enough for them to be disjoint.
It's difficult to, I don't have a conclusive proof. What I'm saying, if you add an additional condition, it becomes easy.
For strict separation, openness is not needed. It's for separation, we need openness. By definition, for strict separation, one f of one convex set is less than 0 and f of the other convex set is greater.
At the moment, I will need that. And then also still need openness to prove.
If they are not disjoint, then there's a common point, and f of that common point should be equal to 0. Lies exactly on the.
It exactly goes like this. We'll see where the openness is required. Okay, so let's try to do that. So what are we given? A chi1 and chi2. And let's say chi1 is only, even though I'm drawing a boundary. Now what am I given? Strict separation. So let's look at any point here. What can I claim rather? So think of the affine function which is the affine function of A transpose X minus B. What should we evaluate to at any point here? Strictly less than 0. Why?
Because there is a strict separation.
Okay. Is that all there is to it? So now take this strict away. Just separation. Okay. So suppose there is no strict separation. What you said is correct. If there is strict, there is nothing to be done. Just separation. And now X chi1 is open. So this one set is open. Let's just follow. Now let's call this point U. All I'm given is there is a separation. I want to claim that given that the set is X is open, f of U is in fact strictly less than 0. Why? For all U belonging to chi1.
Because if f of u is equal to 0.
Yes. Then what happens? The set is open.
Yes.
So suppose the, sorry. Okay. So now suppose if it was touching this function f, essentially what that means is f of u is 0. And this set is open, right? What will it imply? That there is at least some point here for which f of u prime is greater than, sorry, not, this is terrible. At least last semester it wasn't doing this. It is strictly greater than 0 for some u prime belonging to chi1 itself. And that contradiction to the separation. So if at least one set is open, just separation is sufficient for you to produce that they are disjoint. Strict separation automatically gives you the same thing. The same conclusion is drawn by a direct strict separation. That's what. Are you okay with this? Feel free to interrupt me. I'm not in a hurry to go anywhere unless everybody is with me. Is it clear what is going on?
Yeah, I have a doubt about that strict separation.
Yes.
We need
So let's just forget that this is strict. So that is unnecessary. What I'm actually producing is a strict separation via making them, one of them to be open. If it's already open, then everything on the left is less than 0, everything on the right is greater than 0. What I'm telling you is that if there is no strict separation, but the set is open, then it better be strict, essentially strict separation. And then automatically imply disjointness.
Strict separation, we need both of them to be strictly equal, right?
Yeah. One is strictly greater than 0, other is strictly greater than 0.
Yes, but then in that case, for strict separation, we need both of them to be open.
Why?
Because otherwise,
But by strict separation, what do I actually get? I have an hyperplane. Everything on the right is greater than 0. Everything on the left is greater than 0. Then as you said, I can find a point, if they are not disjoint, at which point what will happen? That would be enough to prove this. So it will be disjoint just by the fact that everything on chi1 is less than 0, everything on chi2 is greater than 0.
okay. Yes, but everything on chi1 is definitely less than 0, but
Yeah.
on chi2 it could be greater than or equal to 0.
No, so by definition, for me, correctly, strict separation means strict on both sides.
Yes.
So then there is no question of having anything in between. So everything is greater than 0 here, everything is less than 0 here, strictly. So then there can't be nothing in the intersection. If you take this away, then you might have to add certain conditions. So you're saying half strict, then you possibly have to add a few conditions. But openness is kind of, which makes it work because of the following reason, that if it is not strictly 0, then you'll find something greater than 0.
Yeah, so what I was saying is if only one of them is open,
Mhm.
then that doesn't imply strictness.
That doesn't imply strict. No, no, we're starting with an assumption.
Yes, we started with just a separation.
Yeah.
You mentioned that if one of them is open, then we are essentially making string separation.
What did we do really? Tell me. We started with, let's say, I want to claim that on this side everything is less, on this side everything is.
Good.
Oh, so I looked at a point at which it is 0.
Yes.
This guy is open, so I will find a point which is f of u prime greater than 0, and u prime belongs to chi. So that's not going to happen.
Yes.
So what did I eventually show? That this is true.
Yes.
What is true for any of these points? Just let do this brutally.
It would be greater than equal to 0.
Okay, but that's okay. Okay, it depends on how you want to define this. So now for f of v, for v belong to chi. Okay.
Yes.
Now, according to me, this is not strict. According to your half strictness, this is strict. No. Let's settle to that. Okay, so given the time left, I think it's correct time to define something new so that you can mull it over. The thing which we are going to spend most of our time in this course. So what is a convex function? So function defined from domain to, let's say, R. Domain has to be convex. And what happen or has to happen? Always, I think picture is much easier. Functions of this type, what do they have? An interesting property. X, Y, any linear combination is theta x plus 1 minus theta y for theta 0. What has to happen? The function evaluation at this point is lower than this point and this point. So what will that look like? F of theta x plus 1 minus theta y less than equal to theta f of x plus 1 minus theta. It's always difficult to remember which direction this goes. Always make the picture, never make a mistake. Okay. What are the punchlines? For to be defined to be convex, the domain also has to be convex. The set over which you are defining better be convex. You'll see an example where if it's not, problems start. We'll not spend too much time on that, but just keep in mind that the function definition itself requires the domain to be convex and this property to be true. If everything is flipped, we call the function concave. So that is all. A function can be both convex and concave at the same time because of the equality sitting there. No, not just linear. Because I'm not strictly convex and strictly concave. So a strictly convex function cannot be strictly concave. Okay, so once we define something, what do? We do results. What's the simplest example of a convex function, which you have been taught since high school or even before? By constant 0. F of x equal to 0 for all x. It's a convex function, it's a concave function, it's all possible ways. Fine. Next level. Straight line. X square. What about x cube? What kind of function is x cube?
It's not con, it's partial.
After 0, it is bound.
Okay, very good. So what's wrong with the domain? Domain is minus infinity to infinity, right? That is convex.
It has a
So it's not convex, that's a different story. Okay. But how do you know it's not convex?
because it has a point of infinity. That's why it's big.
Can you be more? So suppose I'm a high school student, how will you convince me just from my definition that that function is not convex? Okay, very good. Keep going.
So f of minus 1 is minus
Mhm.
and any linear combination of minus 1 and 0, suppose it's minus theta itself.
Mhm.
So f of minus theta is bigger than minus theta.
Okay. From first principles, you can do it. You don't have to put any test. Oh, so polynomials are out. Now what next? Because 0, we got x square.
But four also.
So
It's possible.
any even power, I think, is. But is x cube concave? If it's not convex, it's neither convex nor concave. Okay, so look at some other class of functions.
Modules.
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 Absolute value, sorry. Absolute value is convex. Though a dangerous function appears all the time, it's very difficult to handle it because of non-differentiability. You'll eventually someday run into trouble while solving a problem. So that's why all sorts of approximations of it are taken, just to make it smooth around 0. Yeah, absolute value is what else? Anything non-trivial comes to mind. There are thousands and thousands of convex functions. Power x is convex, yes. And how do you show that? Just by some log inequality. What about log?
Log will be like.
See, when I say convex function, it is same as a concave function. No distinction between. So whatever you want to do applies as it is to concavity. We will do one side because we're looking at minimize f of x. For concave function, we are maximizing f of x because minimizing a concave function is hard and maximizing a vex function is hard. So we don't want to do that. Two things: minimize the convex function, maximize the concave function. They're equivalent problems. So we're not going to talk about how to maximize the concave function. We'll just stick to minimize the convex function. So log is a concave function. To minus and you get a convex function. So what else? Log done. Anything which is not obvious. What happens if you add two convex functions? Do they remain convex? Why?
Just adding the
Don't look at it, but give me a pictorial argument. Give me a picture argument to prove that if I add two convex functions, it will remain convex. What will it look like? So, for example, take this kind of function, shift it. When you add it together, does it look like a U-shaped curve? Try to see if I can create something which doesn't look like. This is the obvious example where things, if at all go wrong, will go wrong. So what is, let's call this F and let's call this G. What is F plus G? What does it look like? You can think of F as x square and g as some x minus theta whole square or 1 whole square, doesn't matter. As simple as that. What does f plus g look like?
That is a quadratic with the same kind of.
Can you write it as a quadratic? Don't think. No, quadratic meaning, can you write it as some x minus theta whole square? That you can't do. So now how do you convince me that this is convex? Don't take the second derivative.
Because the coefficient is positive, 2 is positive. The leading coefficient.
Yeah, but something might go wrong here. In the limit, I agree that this will take over. But for small values, this could bother you, especially around 0. Small values of x. This will get suppressed further, while this will take over. So that's not a proof. We'll give you that this is in fact true. So what do you think happens? Is f of x plus g of x always convex? If f and g are? They are. Okay. What about max of f comma g? And then similarly, min of f comma g. And f compose g. So now I have functions, I can do whatever I want. Okay, what will happen? This example is actually illuminating. What will happen in minimum? Let's take, I will go like this, right? This is what min looks like. So clearly not common. What will the max look like? Just this part. This will be the max of it. But that's not a proof. Counter examples are easy, pictures. But in fact, that is true. It is convex. What about composition? And FOG, when I write, it's always G first and then F.
Right, max always.
You need a proof. This is not a proof.
Yeah, so
this is a picture, but it's true.
for this picture.
No. In general, it's true. I've not proved it, but in general, it's true. If you want, I'll prove it. Most likely next class. But it's much easier to actually remember why it is true. This is why it is true. And why min doesn't work. These pictures are like the first thing you should flash in your mind, why max should work and min will not work. What about composition? Can something go wrong with the composition? What should be convex?
Range of
Given. We're not looking some pathological case. How do you actually do the convex function by definition? How do you actually create range of G to be non-convex? So let's say domain was 0 to 1. For 0 to half, you create 1, and half to 1, you create 1. Is that a convex function, first of all? So G is a function from 0, 1 to 1, 2. So any point x equal to 1 for x belongs to 0 to half. Okay, and g of x is equal to 2 for x half to 1. That's what you really wanted when you said, I'm going to create a range which is non-convex. Now it is 1 and 2. But it's G convex. Why?
Yes, but it is having only two elements, right?
It's not a set anymore. We're talking about a function. So it is flat here, and then it's flat here.
This column.
So is it convex or not convex? No longer continuity is not required anymore. You think of unit step function. Is it a convex function?
So, I don't think f of g is convex because I guess e to the power minus 6 squared from that it's
No, this is, I think, much more basic question. Is unit step function convex? Before going there. Domain is all of R. This is 0, is 1. Is it convex or non-convex? Just by the first definition of convexity. Just apply first principle definition. What is the first principle definition? If I take 2 points and look at the linear combination and evaluate the function there, where should it be? Above or below?
The function value should be
Below the chord. So where do it lie?
function.
It's not even convex. So you should object to my definition of that function. If unit step is not convex, that function is only building even more than that. That's also not convex. So first you have to produce to me a convex function whose range is not convex. That's not obvious how to do it. We'll see things automatically. Definition of convex sets will make something work. So yeah, we haven't proved max or FOG or whatever. All of this can be proved, but think before the next class and try to think of non-trivial examples of convex functions. They're not necessarily things you already seen, or you might think that it's convex, but you know that those objects. Just think any object you know. You know so many functions. Think of anything which might be convex.